지난 30년 동안 우리는 다른 별을 공전하는 약 6,000개의 외계행성을 발견했습니다. 그렇다면 천문학자들은 이 외계행성들을 어떻게 찾을까요? 그리고 실제 사진을 찍을 수 있을까요? 이 체이싱 스타라이트 에피소드에서는 가장 널리 사용되는 외계행성 탐색 방법들을 간략하게 소개합니다.
The news is full of exciting exoplanet discoveries. Planets around stars right in our cosmic backyard. Enormous gas giants orbiting tiny stars. And even worlds with possible signs of alien life. But how exactly do we find these new distant worlds? And what are the chances of spotting a second Earth? Finding exoplanets requires some serious astronomical detective work. They're like tiny needles in a giant cosmic haystack. But there are ways in which their presence can be betrayed. One is through minute wobbles in the host star's motion. A planet and its star are tied together by gravity, so each influences the other as they fly through space. The effect of the planet is very small relative to the star, but using sophisticated planet-hunting instruments, we can nevertheless detect these small changes in the star's motion, using something that you've probably experienced here on Earth, the Doppler effect. That's right, the same phenomenon that changes the pitch of a siren as it travels away from or towards you also helps astronomers find new worlds. When a wave of light, rather than a sound wave, is stretched and squeezed, this changes the color that we see. We talk about it being blue shifted when the light is compressed to become more blue, or red shifted when it is stretched to become more red. It was using this so-called radio velocity method that the ESO instrument HARPS made an iconic discovery about a decade ago. An Earth-mass planet orbiting our cosmic neighbor Proxima Centauri and potentially holding liquid water. This was no mean feat, and it was possible only thanks to the sensitivity of HARPS. HARPS can detect stellar motions down to about 1 meter per second. That's about as fast as a brisk walk. But that's not all. Our very large telescope houses an even more, alert planet hunting instrument, ESPRESSO. ESPRESSO can detect stellar motions down to about 10 centimeters per second, and it was used to find a planet around Barnard star, our closest single star that may be stable enough to have allowed the emergence of life in its vicinity. However, there is another method that's more effective at finding exoplanets, and that can provide us with a lot of extra information about these distant worlds. It's incredibly simple. When a planet passes in front of its host star during its orbit, this creates a dip in the brightness of the star, due to our view of it being partially obstructed. When exoplanets are caught in the act like this, we can measure these so-called transits. We can measure how often they occur, how long they last, and how deep the dip is. This allows us to infer the size of the planet, which, combined with the mass, which is available from radio velocity measurements, gives us the density, and allows us to say something about the structure of the planet. Is the planet a gas giant? Is it a small rocky world? Is it icy cold or scorchingly hot? Or are the dips possibly even caused by more than one planet? So far, this transit method has been the most successful way of finding new exoplanets, netting about 3/4 of all discoveries. Compared to other methods, the transit method has the big advantage that you can monitor several stars that are close together in the sky at the same time. While with other methods, you need to look at stars individually. This is what the most successful planet hunter of all times, the Kepler Space Telescope, did. However, the transit method has one major caveat. It requires the planet to pass in front of the star. And we know that only a small percentage of all systems out there do this. So, although the transit method has provided us with many new exoplanet discoveries, we know we're just seeing the tip of the iceberg. ESO's Paranal Observatory hosts 2 facilities dedicated to planet hunting using this transit method. Speculoos, whose name is inspired by a biscuit, and the NGTS, the Next Generation Transit Survey. A few years ago, astronomers used data from these 2 facilities, as well as the Cheops Space Telescope and radio velocity data from ESPRESSO, to find something puzzling. An exoplanet system hosting a whopping 6 exoplanets. But why don't we just find planets by directly imaging them? Well, in some cases we do, but it's really, really, really hard. The problem is that the host stars tend to be much brighter than the planets and completely outshine them, meaning the planets are nearly impossible to catch on camera. Saying that, Exoplanet photography, or direct imaging as we call it, has been used to find a fair share of these worlds. We can get around obstructive starlight by blocking it using a coronagraph. In fact, Sphere, one of the instruments at ESO's VLT, is fitted with a coronagraph, and it was used to take some pretty amazing exoplanet images. For example, this first image of more than one exoplanet orbiting the same sun-like star. And it was another VLT instrument, NACO, that all the way back in 2004 was used to take the first ever direct image of an exoplanet. In the 30 years since the first exoplanet was found, we've discovered about 6,000 new worlds. But there are many more lurking out there. Some of them may even be similar to our own planet. Small Earth-like planets create a less noticeable wobble in their host star. They block out less light and don't show up as well on camera as gas giants, which means that they've mostly escaped our gaze until now. But as telescopes get bigger, better, and more sensitive, this will change. ESO's extremely large telescope, which is set to come online at the end of the decade, may even find that special, small, rocky world nestled in the habitable zone of a sun-like star. The second Earth we've been searching for all along.
인류의 가장 위대한 질문에 대한 답을 찾는 여정은 이제 막 시작되었습니다. 영상이 유익하셨다면 구독과 좋아요로 이 위대한 여정을 함께 응원해주세요.